Now we'll record. Okay. But I just have to say, that we should at least stop and recognize where calculus is, where it comes up. And not just integrals, but improper integrals. In all over in stat, you're doing improper integrals. So, in fact, so statistics in general is a rich area for calculus. I wouldn't mind teaching statistics if I could teach it as a calculus-based course, right? Just like physics. I would never want to teach a physics class outside of being able to also talk about calculus, right? Otherwise, it's just like, what do you say? You memorize this formula. Go ahead. Yeah, that's right? Right. Let there always be sense-making, please. Okay.
Well, every couple days he also says, well, you can use calculus to do this, but we don't do that.
Good. It makes it more fun. Okay, good. Let's think about 1 over x to the p. You did one of these for a in the warm-up, right? So let's just do it once and for all. You ready? Let's just nail every single one of these and have it done, okay? So let's consider this integral first. This is a general integral from some constant a, where a is positive. That's kind of necessary because I don't really want to think about the vertical asymptote on this. I just want to think about the, from some constant. We've often done from like 1 to infinity or something like that. But it doesn't really matter. I mean, the point is, if you start at some positive number and then integrate to infinity, the question is, already, do you have a hunch as to whether you think whether this is gonna converge or not? 1 over x squared did, because we just saw that on the warm-up. We got 1, I think, right? What about 1 over x cubed? Do you have a feeling that will converge? I think maybe if you integrate 1 over x. But let's actually do the work here. So if you do this, that is what we've been doing all along. I'm integrating this function, 1 over x to the p, from a to b, where b is like infinity, right? So I'm just doing the work for you. I have every confidence that you could do this too. Right? Here's the integral. Just raise that power by 1 and divide. Have you done the power rule before? There you go. That's the power rule. It's a little abstract here because we're doing it with letters, but whatever. It's still this is still the power rule. Check by taking the derivative. Isn't the derivative this, that? Great. And now I'm plugging in b and a and subtracting. That's what's happening here. Just study and make sure that every symbol its origin. Yeah. Check my work too. Make sure it's right. And I should ask you, I guess. But so the question is, when will this, in general, now let's start asking the question, will this converge or not? As we take the limit as b approaches infinity. Well, keep in mind that there's nothing here at all that involves b except for the blue term right there. So this hinges, doesn't it? This entire question of whether this even converges to a number or not hinges on this blue part I've highlighted, right? That's the only part that's involved in the limit. So that's the question, is does this converge or not? The limit as b goes to infinity of that. I've decided to rewrite it this way just temporarily. Is that okay? B to the first over b to the p. Well, you know from your pre-calculus knowledge when this converges. It converges if b is a number greater than 1, right? Or equal to 1. Did I say that right? Well, certainly if p is greater than 1, it converges. Does it converge if p is equal to 1? Well, we didn't actually consider that here, did we? We actually did handle that situation the other day, though. Yeah, 1 over p, 1 over just x to the first, 1 over x. We did handle that situation as a special case the other day, didn't we? We did that one in class on Friday. Yeah, it does diverge, and the reason it's a special case is that none of this applies, right? The power rule doesn't work when p is 1. Remember, the antiderivative is not this, it's natural law, right? So we had a little special footnote for that case, and here it is. I think we did this on Friday, though. So it diverges if p is 1, but I hope you see from this argument up here that it definitely converges if p is a number greater than 1. But if p is equal to 1 or less, then then this diverges. Take, for example, if p is 1/2. Then don't you have b over, or say p is -2 or something, right? Even. You'll have something like b to the first over b to the 1/2. Well, what will that equal then? Won't b to the first over b to the 1/2 be b to the 1/2? Well, that diverges as v goes to infinity, doesn't it? So in general, we can combine these results. We have in blue here, I wrote it as a nice result. But in general, we can just come out and say this, that this integral always converges if p is greater than 1. And it diverges otherwise, if p is equal to 1 or less. You see how we can do this? We can like say some more general things today. We want to kind of step back and develop some intuition about this. And maybe be able to like, I don't know, before we even start the problem, know that it's going to converge or diverge. So you don't need to have like every little piece of this discussion. This is the big result that I'd like you to have in your arsenal down here. But if you ever needed to prove the result, I think we've provided enough proof of that right here on this slide. Question? Huh? The clock is still on. That's true. Nobody notices though, because no one looks at the hour. I'll fix it. Oh my God! What is 19?
Yeah, it's nice.
All right. Similar. I don't need you to. We don't need to go through the proof. If you'd like to, you can. It feels almost identical, right? Just do it kind of with symbols and show that the same kind of thing happens here. So this is the one. That's the one we just said, right? A greater than 0 converges. Okay, that's the one we just said in blue. How about this too? What does that saying? Study what that says. We have a pretty general result here. That's from 0 to b. Why is that even an improper integral at all? Again. Right, because this time this is like the type, I think we call it type 2 on Friday, right? This has a vertical asymptote. So the question is, can we say some general, just like we just talked about a second ago, can we make some general statement about those too, if they're of the form 1 over x to the p? And the answer is yes. We can, and it's very similar. I don't want to go through it again. It's very, very similar. In fact, you can make another argument maybe based on the inverse, right? Approaching 0 is a lot like the inverse approaching infinity, right? So you could like flip and look at it that way. You could make a quick argument based on this result and just expand this result to this case if you wanted. And then I'll give you one more too, which again, actually, I think you could show as well. This is e to the, how do we handle that situation? That came up on Friday in the homework. And again, I'm just going to tell you right now that if you have an intuition about this, you could prove it if you like. That this does always happen if you have e to the c x, and I guess you could say more generally, any exponential decay function. Because can't every exponential decay function be written in this form? I mean, we're just talking about exponential decay functions in general. Do have integrals that converge. So we'll just now like be able to use those results. This is good, right? You ever see one of these that you know diverges? You could just say, well, I know all integrals of this type diverge. You might be able to weed those out right away. So feel free in your free time to prove the other two statements, the red and the green. You know, during So we've already like the third one, the warm up today. You know, we do see integrals that we'd rather not evaluate sometimes. Here's one, for example, that I don't actually know the antiderivative of, and yet I think that I know that it. Well, what do you think? Do you have an intuition? It's not. Let's just be clear. It's not of any of the forms we just gave on the previous slide. Sad. But do you have a hunch? What do you think? Which one does it feel like? Well, okay, it looks like, I'm just thinking of which of the integrams that we studied in the previous pages it feel like, and which of the integral setups. Yeah, it feels like the first case, doesn't it? Except there's like that pesky +1. So I think my hunch is that it converges, maybe. I don't know, that's just a hunch. Let's see if we can actually formally say something about it. We don't know how to evaluate it. But we do know how to evaluate this guy, right? And we do know that that converges. Well, let's study the picture here for a second, and maybe we can do some kind of a comparison between these here. We already showed that one converges. I think it's easy to see, either using a very, very short algebraic argument, that this is true, that this integrand is always greater than this integrand. Do you agree? It's as simple as seeing that the denominator here is bigger, right? So this is a smaller fraction than this. Or you can look at the picture if you like. Isn't the red function always above the blue function? Okay, well, if you know the red integral converges, that is, if you know the area under the red curve is a finite number, then the blue curve has area under it clearly less than this integral, and this is a finite number. So I think we've just shown then, if we can just justify using this picture by proving that, I mean, this is the big observation. If you can agree to that, then I think like the nails are in the coffin, right? This integral must converge also. So maybe we don't know what it converges to, but we can walk away saying that it converges. Sorry, I'll put that back up for a second for what you think about what we just said. You see the big realization today? We can use the three results we just had. You might be thinking a second ago, you'd be like, well, those are powerful and interesting, but they're not that powerful. Well, actually, in some ways they are. If we can, even if we have functions that don't look like those, sometimes we can bring those conclusions to bear on other functions that look similar, at least, and do some kind of comparison, which is the title of today's lesson, right, is comparison tests, right? Can we make conclusions about integrals even though we don't know how to integrate them? And the answer is yeah, like this one. By the way, does this feel familiar at all? A little bit? Yeah, there's definitely some overlap, and we'll talk about the connection between this and series, of course, very soon. But these do sound familiar. I mean, I think you might have thought about the comparison tests with series convergence as well last year, maybe. So we'll make that connection soon. We get to be more theoretical this year, though, about it. And it all comes from this. There's not a single piece of the mathematics today, hopefully, you don't understand. We trace back to first principles. Whereas last year, I think we just told you, maybe we just told you that was. But why should integrals at all relate to series? Well, we'll get to that, not today, but soon. So this is the direct comparison test, which is what you just did with me a second ago. And if you're solving one of these problems, here's what I would expect you to write. I would expect you to write something like this for the last problem. Since this converges, and since this is always less than or equal, since the thing we're looking at is always less than or equal to the known thing that we always know converges, then it must be true that this converges also by direct comparison. That's the, in quotes here, I put it in quotes to just give you an example. That's the kind of thing we would expect you to write for a problem like that, right? Name the test, state the inequality on the interval of interest, say that it converges, therefore this converges too. The direction of the inequality obviously matters though. And that's what this box says. If this is true, then these are true. If in the last example I have 1 over x to the 5th plus minus 1, then this doesn't really, can't really help you here, can it? If we have a function that's bigger than a known convergent integral, Well, I don't have anything to say about our integral. And I'll just put that note again here. I already said this, but obviously we don't. Sometimes we can say it converges, but we don't know what it converges to, and that's fine. And that's fine. So the example we just did falls solidly into the first bullet point here. Right, we have a function inside of another function. The higher function converges, so the lower must too. But of course, we can make a similar conclusion about divergent integrals as well, right? If you have a divergent integral and that you know is divergent, and then someone brings to us a new integral out of a function that's in all places larger than our function, well then yours must diverge too, right? Yours is always bigger than mine. Go ahead, Josh.
I wanted to ask, with the example with 1 over x
Hmm?
with it, would we have to prove why that converges?
That would be fine, right? That what we just said. This is what I expect to see. Yeah. So we all take for granted that the blue, red, and green things I said on the previous slide a while ago, right? That this is true. That is, I think we're all going to just take as a thing we've proved once in our lives, because you just did a while ago. So we all take that for granted that this is true, that the integral from 1 to infinity of 1 over x to the 5th dx converges. And then if this, then you do need to say this. I don't know, maybe you're asking too, do we need to prove this? Well, the proof of this in this particular case, the proof of this is very easy, right? It just follows immediately from the fact that x to the 5th plus 1 is greater than or equal to x to the 5th. Divide both sides by both sides, and you get this, right? Immediately. Yeah, so there's not much to prove there. Okay, let's take a look at these two. Yeah, clearly both are ones that we don't plan on symbolically integrating, right? I think we all agree that we won't be doing that. What are you going to compare it to? Right? Come again? I'm not sure that's a great strategy on the first one. I don't know how to factor the denominator, for example. I guess you want to think for each of these, what does the integrand feel like? Does it feel like one of the things one of the forms 1 over x to the p? If so, for what p? Can you compare this to one of them? What would you like to compare this first one to? This guy here. Yeah, the first one. I mean, but which one? 1 over t to the what? I mean, it seems like some of you are saying different things. Like I've heard 2, 3, and 4. I don't know. This does feel like, especially if you are ignoring these pieces, this does feel like 1 over t squared, doesn't it? So I think that's a good strategy. Can you convince yourself that this is, well, if it's 1 over t squared, which does that do? Does that converge or diverge? The integral of 1 over t squared from some positive constant to infinity converges, yeah. So I think I have a hunch. Have you started developing the hunch, like we talked about? Okay. I think I have a hunch that this converges. Well, let's just write it formally. Can you convince yourself that this is always, which do we need to say? This is always less than 1 over t squared? Is it? How can you convince yourself of that? I mean, we were tricky here, right? This can be negative, that's true. So that's a problem. And sometimes maybe it's not great, or I don't know. Help me out here. Yeah, Nicole. Is better than is less than 1 over t cubed. I think you'd have a little bit of a harder time justifying why that's true, even though I think you're intuitively right that after some point that works. Yeah, it's a little harder to like prove that that's true. I think though. I don't know. Do you just feel that that's true? It seems true. Yeah, I think you're right. It's just I might have a hard time proving that. I don't know. T cubed is it actually, and also it may, yeah. Trying with this. It's possible that could it be possible that that's not even true? I have to think about what that. Yeah, it should be. I think that might be true. Yeah, I don't know. Can you convince? I guess like my thought is, can you convince yourself that t to the fourth plus t 2t plus cosine t is greater than or equal to t to the fourth? Because if we can do that, then I think we've convinced ourselves that this function here, the whole function, is less than t squared over t to the fourth, right? If this down here, and I guess really that amounts to, doesn't it, asking, is this true? Is it? For these values, 1 to infinity, is that true? I think it doesn't take too much work to convince someone of that. Just, if it hasn't come to you yet, just think about it for another 5 seconds. Especially considering the values only 1 to infinity. This is always greater than 2 for those values, isn't it? Does that convince you that this is always positive? Okay. So if that's true, then I think we've convinced ourselves that that this does converge, that this is for sure always less than 1 over t squared, and then we're done, right? So I'll write something similar to what I wrote in quotes on the previous page, and I'd like you to write something of this kind too. Since the integral from 1 to infinity of 1 over t squared dt converges because p is equal to 2, which is strictly greater than 1, right? That's our test from earlier, right?
We have to write that on.
Yeah. Oh, this part? Yeah, I think I would. Yeah. Did I not on the last one? Oh, shame on me. Okay. I mean, it's not always true that something of this form converges. It's only if it's greater than 1. And t squared over t to the fourth plus 2t plus cosine t is always less than or equal to, I mean, that's the only demand we need, but you could just say strictly less than 2. 1 over t squared or t between, what are we doing? From 1 to infinity. It must be true that this integral also converges by direct comparison. How do you feel about the next one? What are we comparing this one to? Yeah, 1 over root y, maybe, right? It feels like this should do whatever that does, maybe. So since the integral from 4 to infinity of 1 over y to the 1/2 diverges because p is a half, which is less than or equal to 1. And can we convince ourselves that this is true? That root y, 1 over root y minus 1, the thing we have, is always greater than 1 over root y for y in the interval? like to at least show you. I'd like to show you the limit comparison test too. Let's see if we can get that up here. So in this example, this is the one. This is an issue for us a little bit because this is 1 over x is the thing we'd like to compare this to. But this is 1 over x diverges, and this is smaller than that. So you can see how our technique like kind of fails here, right? The one we've been using so far. So certainly you can compare it to something else if you like. So this is me comparing it to 1 over 2x. Do I know that 1 over 2x diverges? Not really. That's not something we said today, is it? That 1 over 2x diverges. There's so much more to say. It's all right. All right. Well, you've got a lot to do, a lot of power on the homework tonight. We still do need to talk about one other comparison test called the limit comparison test. But you're doing well.